In this lab, you're going to be looking at the mean value theorem. And just as a refresher, the mean value theorem says if a function f is continuous on the closed bounded interval from a to b and differentiable on the open interval a to b, then there's at least one number c in the interval of ab such that the derivative at the point c is equal to f of b minus f of a all over b minus a. What this means in terms of the geometry of the function is that there's going to be a place, a value of x, that's somewhere between a and b, where the line that's tangent to the graph at that point is parallel to the line that goes through the endpoints of the interval, which we would call a secant. So let's visualize that on a graph. Here I've created a curve and I've set up an interval from A to B, and the only part of this curve we're going to worry about is that section from A to B. I isolated the part of the function that we're looking at. The mean value theorem says that this point C, which I can move along the interval, will have a tangent line that's parallel to the line that goes through the endpoints, which again is called a secant. So let's draw that secant in. Now I'm going to add that tangent line at point C. You can see that where C is located right now, my green tangent line is not parallel to my blue secant, but I should be able to find some place in between A and B where they do end up being parallel. And that happens here. Up here, this m equals 0.5, that's the slope of the blue line, and you can see that the derivative at point C, which is the slope of the tangent line, is also 0.5. So I was able to find that one point C, where the slope of the tangent is equal to the slope of the secant line. There can be multiple C values on an interval, but there will definitely, according to the mean value theorem, always be at least one if your function is continuous, meaning it's traceable, and it's differentiable, meaning you don't have anything like a corner, a cusp, a vertical tangent that would stop there from being a derivative. This also has another meaning, which we'll go back and look at on the other screen. Okay, so here is how the mean value theorem is stated as a formula, but I want to just explain this a little bit more clearly. On the left-hand side, you have the derivative at point C. So this, because a derivative is a slope of a tangent line, is the same as the slope of the tangent line at C. The right-hand side should look vaguely familiar. What you're actually seeing here is a version of the slope formula, where you find the slope by subtracting the y-coordinates over the x-coordinates. In this particular case, we're using this first endpoint, which has the coordinates a and f of a, and this endpoint, which has the coordinates b, f of b. And we're finding the slope, f of b minus f of a over b minus a, of the line through those points. So on this side, this is the slope of the secant line that passes through these points. So this is what we saw on the graph, that we can find a point C such that the slope of the tangent line at point C will be the same as the slope of the secant. So the formula just says in symbols what we just observed in words. The important consequence of this is the derivative, in addition to being the slope of the tangent line, is also the instantaneous rate of change. It's the rate of change that's occurring at that particular moment in time. Compare that to the slope of a secant, the slope that passes through 2 points. This is known as the average rate of change. So another way to express the meaning of the mean value theorem is that you're locating a place where the average rate of change and the instantaneous rate of change turn out to be the same. So for instance, if you were traveling down a highway, all right, your position function with respect to time would be continuous. It would be differentiable. There's nothing going to be weird happening in the graph. And what this is saying is if I calculate when you pass through one toll, for instance, and then arrive at your next toll booth, I'm able to calculate your average rate of speed by knowing how far apart they are and how long it took you. So if I calculate your average rate of speed and it's 75 miles an hour, then what the mean value theorem says at some point between that point A and point B, you were traveling at that exact speed of 75 miles an hour. So theoretically, the police should be able to ticket you just based on knowing the mean value theorem without having to clock your actual speed. So let's do an example by hand before we see how to do this with Mathematica. So I'm asking you to use the function f of x equals x cubed on the interval from 0 to 2. So there's my a and my b. A says, show that the function f satisfies the hypotheses of the mean value theorem on the given interval. Again, you have to check two things before you use the mean value theorem. Then we're asked to find each value of c in the open interval a, b that satisfies the equation f prime of c equals f of b minus f of a all over b minus a, and draw your solution on the graph provided. So the two conditions that we have to check for the mean value theorem are whether it's continuous on the closed interval and differentiable on the open interval. Because this is a polynomial function, it's an x cubed, it's very well behaved. So it is both continuous and differentiable. All polynomials are that way. So I would make that argument. I would say since f of x is a polynomial function, it will be continuous. And it's important to state that it's on the closed interval and differentiable, no corners, cusps, vertical tangents, discontinuities on the open interval 0 to 2. All right, for part B, we need to do the actual math of working with this formula. So I'm going to begin by writing out my formula. And you're going to get to work on the right-hand side. We know our A and B because they were given to us. So I know A equals 0, B equals 2. I now need to find f of A, in other words, f of 0, and f of B, which is f of 2. And that's easy enough to do because I've got the original equation, so I'm just going to substitute in there to get my values. Now I have all the values I need to substitute in the right-hand side of the mean value theorem. So as you can see, I've substituted my A and B values, then substituted the f of A, f of B values, reduced it, and I get a value of 4. Now we're ready to start working on the left-hand side. If I want the derivative at point C, I would begin first by taking the derivative of my original function. So if my f of x equals x cubed and I take its derivative using the power rule, I would get 3x squared. Multiply the exponent by the coefficient in front, lower the exponent by 1. Now, if I want to take the derivative at point C in particular, I just substitute C in place of my x. And that gives me this equation I substitute here. I'll carry it down until I get to the simplified line. Now all that's left to do is solve for C. Easiest way to do that is to get rid of the 3 coefficient by dividing, and then I need to take the square root. The important thing to remember here is because I introduced that square root, I need to consider both the positive root and the fact that there could be a negative root. However, if you pay attention to the fact that we're working on the interval from 0 to 2, this negative value will not show up between those numbers, so I'll end up rejecting it. It is important to remember to consider it, though. So I have found the C value where the slope of the tangent should be the same as the slope of the secant that goes through the endpoints. I typed it into a calculator, and it's approximately equal to 1.15. And if you look at our scale down here, here's where 1 would be located on the x-axis. So 1.15 is just a little nudge ahead of that. So what I have determined is at this point, if I draw the tangent, it'll be parallel to the secant. First, I'm going to attempt to draw my secant, like so. And now I'll draw the tangent. And it does appear that the tangent that's located at that C value is in fact parallel to the secant through the endpoints. Okay, so that's what mean value theorem does. Okay, in this Lab 9 demo, we're going to talk about how to do these various steps of the mean value theorem with Mathematica. So the first thing we'll do is write the equation of the line that passes through the endpoints of the interval. And we're going to use the same example that we worked out by hand. I've restated over here on the left the mean value theorem, and I've reminded you that the right-hand side is the slope of the secant. So if I want to write the equation of that line, I need a point and a slope to use point-slope formula. So I will begin by storing my function. And then as we saw before, we needed to find what f of 2 and f of 0 were to be able to substitute them into this right-hand side. So you can just ask Mathematica for those values, or alternatively, you can type in that whole right-hand side with the a and b substituted, and it will tell you the value of that side. So I technically have the coordinates of 2 points. I have the 0.28 and the 0.00, and I just calculated my slope to be 4. So I can use either point when I'm writing the equation of the line, and for obvious reasons, I'm going to use 0. It just makes life easy. I put in when I simplify this equation, I get y equals 4x. Now this is going to need to be stored in Mathematica as well as my function g. So I have stored my secant line equation, and just to make sure that it looks like it really is the secant, I'm going to do a very quick plot command with my original function f and my function g, only from 0 to 2. And you can see it does look like that orange secant line is going through the endpoints of the curve. Now I would want to write the equation of the line tangent to the curve at point C. That's guaranteed to exist by the mean value theorem. In order to do this, I need to solve for C first. Here I am back at my mean value theorem, and remember the left-hand side is the slope of your tangent line, and that's what I'm reminding you of here. The slope of the tangent at point C is the derivative at point C. So I can type that into Mathematica, and it will tell me that that's equal to 3c squared. So that's the left-hand side of my mean value theorem. And remember, we just saw that the right-hand side, the slope of the secant, was 4, which gets us to this point in the process. Now, we did the algebra by hand, but if you're using Mathematica, you can use the solve command to solve that equation for you. Notice it does bring up both roots, and I am going to ignore the negative because of the fact that the interval goes from 0 to 2. I should also mention that 2 over radical 3 is the same as the square root of the whole fraction 4 over 3. So here's what I now have towards writing the equation of the tangent line. I know the c value, that's going to be the x coordinate of the point, but I don't know its y coordinate, and I don't know the slope. I can find those things again using Mathematica, if it lets me. To find out the y coordinate, I'm just going to plug my x value into the original function, and here is its y coordinate. So I now know y is 8 over 3 square roots of 3. Next, I need to know the slope. The slope of the tangent line is the derivative at that point. So I will go to a new line, type in the derivative, and put in 2 over square root of 3 again. Again, this time I'm doing derivative because I want to know the slope. And apparently the slope is 4. So I have y minus equals my slope of 4 times x minus 2 over radical 3. And if I solve for y, I would boot that whole fraction over to the right-hand side, and it would become addition. So there's my equation. I will now store that as function h. And one more time, I'm going to just plot that with F and G so I can visually verify that it looks like I have done the mean value theorem correctly. And you can see it does look like the green line is the tangent to the curve, and it's parallel to the orange line, which is the secant. Well done.